Hello, welcome to the video. And before we analyze, let's take a look at stage 3 feed forward opamp. So until now, we have discussed stage 2, in which we had two stages cascaded. So basically, um, when we say that we use an integrator to push a current into GO1. So while making an integrator, we made this integrator of single stage op-amp, and now we have an idea of making this integrator itself of two stage. So in total, it will become a three-stage op-amp, and this is a layman idea. So let's work towards it, and we have the integrator which pushes the current and which is basically of two stage. So in total, we have a three-stage feed forward op-amp, and let's look at the transfer function of this op-amp and stability criteria as well. So let's name all the OTAs or transconductors as GMs, and this is how our circuit will look like, and it is pretty much complicated, but let's say that while deriving a transfer function, we have two currents coming at the out node, and so just like second stage feedback op-amp, first we see GL in parallel with CL, and we have two current contributions. So these are the two current contributions, and one from GM1 and one from GM5, and contribution from GM5 is nothing but the contribution from GM2 and the contribution from GM4. So again, we can say that contribution from GM4 is nothing but the contribution from GM3. So while deriving the transfer function, we can say that contribution from GM1 is basically GM1 divided by the conductance associated with it and multiplied by the input voltage. And now similarly, we can say from GM5 we have two currents, and these two currents are basically this one and this one. So what are these currents? So basically these are the one coming from GM2 is GM2 divided by the conductance associated with it times the total voltage, and similarly coming from GM5, and the current comes from GM5 over here. So this current is totally given by this, and the contribution coming from GM4 is nothing but GM3 divided by the total conductance associated with it multiplied by GM4 divided by the total conductance times the GM5 divided by the total conductance associated with it times VE. So this is the current coming from GM5. So basically, this is our whole transfer function, and this part is coming from GM1 and this part is coming from GM5. And we can say that let's divide our transfer function in three different parts, and these three different parts are F1, and we have F2, and we have F3, just for the sake of simplicity. And by looking at this transfer function, we see three poles and two zeros. How? So we have three poles, and when we make the denominator equal for all the terms, we get a quadratic equation in the numerator as well, and that gives us two zeros. And from here we can see that our poles lies at the values which are GL by CL, GO4 by CO4, and GO3 by CO3. So basically, let's assume the op-amp is in unity gain feedback. So where k equals to 1 and omega loop equals to omega u, and it is put in a negative feedback. So let's talk about the stability about it. So we have our transfer function which is divided in F1, F2, and F3. So let's plot curves for these. So we have F1 and we have single pole associated with it. So this is the function of F1 where we have our first pole, and then we have a minus 20 dB rule off. Then we have our F2 where we have two poles, and thus pole 1 20 dB minus 40 dB and so on. And then we have F3 which has three poles, so pole 1 minus 20 minus 40 and minus 6 dB rule off. Now our transfer function is not f1 f2 or f3, it is an addition of f1 f2 and f3. And in such a case the curve follows whichever the highest value it has at that particular point. So basically the curve will follow this curve like this. So in addition, and it is a logarithmic values, so this is how the curve follows. And over here in this part function 3 is dominating. In this part function also in this part the function 3 is dominating. In this part we can see function 2 is dominating, and in this part function 1 is dominating with a higher value. So this is how our curve will look like, where we have our unity gain bandwidth or frequency over here we have. And from here we can say that we had a minus 60 and it went to minus 40 dB roll off. So we can say that our 0 will lie over here. Similarly, from minus 40, it went to minus 20. So we can say that our second 0 will lie over here. So we can say that lower frequencies, at lower frequencies in this range, function 1 dominates. At mid-range frequencies, function 2 dominates, and at very high frequencies, function 3 dominates. And thus, this is how our phase plot looks like, in which there is 3 times minus 90 degrees phase lag due to 3 poles, and due to 1 0 again a lead of phase, and again a phase lead due to 0 2. And now at the point of omega u we have pretty much good phase margin. So let's see Nyquist plot for the stability. So in this case we can see that at omega u we have pretty much good phase margin, and there is no encirclement in our Nyquist plot. So while we are plotting our Nyquist plot, so we start from here, then it approaches the center of the circle, but due to the first 0 it again goes out, and due to the second 0 again goes out and approaches the center from here. So in this case this phase margin I think is pretty good and the system is stable. But now while talking about stability, we have to consider the cases where k is not equal to 1 and a negative feedback loop has a higher value of k. And what happens, so we made an op-amp saying that it's stable, and by taking np minus nz, so basically number of poles minus number of zeros equals to 1, which are occurring before omega u. So when we place it in a negative feedback loop with k equals to some value which is not equals to 1, obviously it is higher than 1. So we have this curve for k equals to 1, and when k is not equals to 1, so our gain, DC gain, is divided by k, and which is basically our loop gain. So it is basically this curve, where we can see that this curve is hitting the 0 dB axis at the lower frequency, where as compared to the curve which had value of k equals to 1. So basically what happens at this point is, we were looking at phase margin over here, now we have to look at phase margin over here, and we can see that the phase margin is negative. So when, like, we can say that when the value of k increases, so omega loop shifts to the lower frequencies, and the phase remains the same. So the phase plot shows that when k increases, the phase margin actually decreases in this case, because we are getting a negative phase margin. So when we plot the Nyquist plot for this, so we start from here, but the thing is we enter the unity circle from the negative side from here, and this gives us instability. And here, as the due to the curve is encircling in a clockwise direction, the critical point is actually getting encircled, and here our system is unstable, and omega loop obviously has a lower limit for the stability. So we can say that we will get a conditional stability when we increase the number of poles before omega loop. So yeah, we can have the more number of poles before omega loop, and we also say that we have this criteria that to make it stable, just make the number of poles minus number of zeros equals to 1. But along with that, we also have to look that omega loop has its lower limit as well, and we are getting a conditional stability. So let's compare the Miller compensated op-amp and the feed-forward compensated op-amp. So in the Miller compensated op-amp, we said that for k equals to 1, the curve is like this, and our phase margin is nothing but at 90 degrees. So even though we said that our P2 should lie at higher frequencies than omega u, and only the dominating pole or the first pole should be beyond omega u, and all other poles and zeros should be after omega u. So at this case, we have a phase lag of 90 degree only, and our phase margin is secured. So even though we have a higher k values, and even though our omega u is shifted towards lower frequencies, still we will be getting good phase margins. But in the case where we just saw, in the case of our feed forward compensated op-amp, if we shift to the lower higher values of k, or let's see, when our omega loop shifts to the lower frequencies, so at the same time we will be getting instability due to the phase margin. So we can say that our feed forward compensated op-amp is conditionally stable, and our Miller compensated op-amp is unconditionally stable when it comes to this kind of analysis. And so in case of Miller compensated op-amp, for k greater than 1, it is always stable. And if it is stable for k for 1, for k is equals to 1, we can say that for higher values of k, it will always be stable. But if we have feed forward op-amp, so working well for like k equals to 1. So let's say our feed forward op-amp is working very nicely for k equals to 1. That does not always mean that it will work for all the values of k which is greater than 1. We need to design specifically for whatever k we want. So we can have many poles and zeros before omega u. What matters is at the omega loop, we have the effect of a single pole, and due to that single pole effect at omega u, we have to analyze our stability. So I think we have discussed in brief about feed forward compensated op-amp, and that's all for today's video.